Okay, hello and welcome back everybody. Moving on to the next chapter, looking at parametric and polar behavior in the plane. By the plane, really what I'm saying is two-dimensional. And maybe if you don't know the word parametric, we'll discover it eventually. Polar we did already see in this course. If we went back to the complex algebra section, that's where we were thinking about a coordinate system where instead of a grid-like pattern that we assigned to the x and y directions, we are thinking about moving around out some radial amount and then around an angle amount. So a radius and an angle describes all of space is what polar means. But in a lot of ways, what we're going to cover today, trying to link everything together, we're going to basically use dynamics as this foray from one dimension to two dimensions and really give us a reason why we should study parametric and polar behavior in two dimensions. So today we're going to study dynamics in two dimensions. And really what we want to think is that we have very similar properties to what we saw before of the continuous and discrete dynamics. And we can define them in the exact same manner, except we're going to have to define our functions. Let's recall what a dynamics in one dimension was a function of a position and a time window that satisfied special properties of composition, as well as being the identity when the time window was degenerate. We're going to get the same thing out of two dimensions. It's just that the one dimension in the one-dimensional dynamics was the fact that I was only dealing with a single position evolving over time. So I'd say one-dimensional dynamics considered only a single position or measurement, whatever you want to think about it, which would evolve over time. In two-dimensional dynamics, we can basically just say, hey, I'm going to pair that first position I was measuring with a second position that I'm measuring. I'm going to call it y, and kind of this two-dimensional coordinate or this two-dimensional point can evolve over time. So I'll say now in two dimensions, we consider 2 points, two positions or measurements that are evolving over time. There's some sort of identification that the two measurements are linked together, right? So we can describe maybe a spider crawling up a wall. Its left-right direction and its up-down direction on the wall both depend on really what the spider is deciding to do. It can kind of evolve around the wall in any direction that it wants to. This could be the same as if you were maybe looking down upon a city and seeing cars drive through the streets, right? The cars can drive in the forward, backward, or left-right directions within the city. So anytime we have really two positions or at least 2 degrees of freedom that an object can evolve around, that's what we're thinking about with two-dimensional dynamics. But the way it's written, and this is once again a kind of a garbage collection of symbols, but it means something important. The way it's written is we think about a function. Okay, this function is going to be f, and f is, it makes a little bit more sense if I look at this bottom one, f is a function of the two positions as well as a time window, and it needs to satisfy the two properties that, hey, if I put one copy of f into the position measurements of another copy of f, and so long as the end of the first time window is the same as the second, same as beginning of second time window, we should think about what is this describing. It's like me tracking the position of the spider on the wall from when I start looking at it to 5 seconds later. Well, it's moved to a new position. That new position is what this is referring to, and then maybe I wait another 5 seconds and the outside f is referring to, well, it started at its new position of wherever the first 5 seconds brought it, and then the outside f has moved it to a later position. But if somebody else wasn't tracking its movement right in the middle after 5 seconds and they only tracked it over 10 seconds, then they would be looking at this sort of behavior, and we should both agree on where the spider ends up after 10 seconds, regardless of how many times, how many kind of subsets I'm mapping its position. If I look at 5 seconds and 10 seconds, or my friend who just looks at 10 seconds. And so it satisfies that same property that more or less, if you look at the time windows and the inside terms are next to each other, they're both going to cancel each other, and we get kind of the bigger time window that just includes the lower time there and the upper time there. And then it also needs to satisfy the most natural property that says if I ask where the point xy has moved after no time at all, it had better not have moved at all. And that's why we have, xy as the input is the same as the output. This is that the point that we measured the spider at right away, if I wait no amount of time, the spider hasn't moved at all. So this is the same sort of idea of dynamics that we had when we were working one dimension. I've just kind of modified that position input now to have two variables inside of it, because it's going to take points and allow the points to evolve over time. Discrete dynamics is going to say the exact same thing. We're basically just replacing our time windows that were allowed to evolve as a subset of R, and now we're going to allow our time windows to be discrete and evolve as a subset of the integers, just as we saw before. But I mean, the primary difference of this chapter is that now I'm working with two-dimensional inputs, right, x and y. And then here's my, my discrete time window. My discrete time window, the n1s on the inside, as always, are going to cancel, and we just end up with the bigger time window. As well, if I have a degenerate interval and no time moves, then I end up exactly where I started. Not really anything new there. I've got an example of two-dimensional dynamics, both the continuous and discrete setting, and really we're not going to discuss showing that something is a dynamics. We already went through the work in one dimension. It kind of looks the same in two dimension. You just have a lot more terms sitting around, a lot more algebra you have to go through. It's quite the tedious process that we're just not going to worry about. What we are going to worry about is an idea of plotting two-dimensional dynamics, right? Plotting is kind of what I'm going to focus on for this chapter, some sort of visualization of these things, because visualizing two-dimensional objects is quite the important mathematical skill. I mean, this is why geometry is what it is, at least two-dimensional geometry. So what we have here is a dynamics, and you'll just have to trust me about that, but this function takes in a point x and y, and it outputs, if we look very carefully before this comma shows up, this is the output as an x coordinate, and then we have our output as a y coordinate. So what we want to think is that an x went into it, a y went into it, that was some original point in two dimensions, and then we weighted this positive amount of time between our initial time and time t, and that point, the x value of that point, has now moved to this, whatever this number is, because you can just calculate it as a number that depends on my four inputs, and the y value of that point has just evolved into this value, which is, again, just a calculation involving the four inputs. And so that's how the dynamics, in our case, is going to look, and also in this case, it is what we're calling a logarithmic spiral that you'll see later. If we actually want to plot this, we only have two dimensions at our disposal, and there would be infinitely many choices of initial positions that I could put in. So what I'm going to do is I'm going to make a very specific choice on the initial conditions. I'm going to make a specific choice that x is equal to 1, y is equal to 0, and my initial time is equal to 0. And if I just go ahead and look at the output of my function, and at each x, I replace this with a 1, so that's going to be a 1. That's going to be a 1. At each y, I'm going to replace it with a 0, so that's going to be a 0, and that's going to be a 0. And every t0, I'm going to replace with a 0, so that'll be a 0, a 0, a 0, a 0, and a 0. What I end up with is kind of this output here, which has simplified quite a bit. And so this is a two-dimensional point which evolves over time. That's how we should think about it. It's a two-dimensional point that evolves over time. If I look closely, this is the x-coordinate of the point, because that comes before the comma, and then this is the y-coordinate of the point. And so what I'm going to do to actually kind of get a representation of this is I'm going to choose a specific number, right? We would love to choose infinitely many values of t, but we don't really know how to do that. So instead, we're just going to choose finitely many values for t, and we're going to kind of evaluate all those t's here, 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 and here, and get a lot of values for x and for y. So what I'm going to do here, if I scroll up a little bit, suppose I had put t equals 0 in, and let me write out my output again really quick so we don't lose it. E to the t cosine t minus e to the minus t sine t here. That's my point. So if I had plugged a 0 in for t, 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 and t, well, e to the negative 0, or e to the 0 will be 1, cosine is 1, sine is 0, so because the x-coordinate would give me e to the negative 0, cosine 0 gives me 1. That's why I have an x-coordinate equal to 1. If I compute the y-coordinate, negative e to the negative 0, sine 0, because sine of 0 is equal to 0, the y-coordinate is going to give me a 0, and that's why I've placed a 0 there. I could repeat at pi over 4, and of course this is my e to the negative pi over 4, and then I kind of have my cosine pi over 4 there. I have a negative e to the negative pi over 4 and a sine pi over 4 here. I've just continued with pi over 2, I've continued with 3 pi over 4, I've continued all the way with all my lovely pi over 4 portions of the unit circle up to 2 pi, where I end up at e to the minus 2 pi in the x-coordinate and 0 in the y-coordinate. And now that I have evaluated kind of this function that had two terms separated by a comma at many values of t, I'm just going to pair the x and y terms together into a collection of points. Okay, so I've got these paired as points, and to plot everything, I'm actually going to go ahead and forget that time was evolving at all. I mean, I would love to have, instant video available to me, but certainly we didn't have that back 100 years ago, and we're still probably a little bit of ways away from it. So we're just going to forget about t when we plot. I'll describe when we look at the plot where kind of t is hiding behind the scenes, but for now we're just going to pair each of those x's and y's as a collection of points, and now we can just go ahead and plot these points on the xy plane. And maybe to plot those on the xy plane, I've gone through a little bit of work and calculated them as decimals here, so you can see that I've actually done a good job entering all of these on the plot. But if I include all of those on a plot, here they are. So this was the first point I calculated, the second, the third, fourth, fifth, sixth, seventh, and so on. And what we want to do at this point, more or less, is smoothly connect the dots in order. So it's important that I remember the order that I computed the points, but if I smoothly connect the dots, we do see, this is why we're calling it a logarithmic spiral. And there I've actually provided a logarithmic spiral as well if we connect the dots. Something cool that happens when you deal with dynamics, specifically dynamics in two dimensions, is that if we start a two-dimensional dynamics from different initial values, their trajectories will never intersect. And so you can get some very pretty images by choosing kind of a symmetric collection of initial conditions, and then these lines, these trajectories always have to intertwine each other in really kind of cool ways because they can't intersect. That's something that's really cool about it. And so it's fun to see them kind of work their way around each other. In this case, we ended up with a bit of a rainbow pinwheel. Okay, let's move on to the next example where we're going to learn about plotting a two-dimensional discrete dynamics. Let's just recall that what's special about discrete dynamics is that the time steps must be integers. And so like 1, 2, 3, you can't have something like 8 halves for a time step when it comes to discrete dynamics. And so what's going to happen here is we've constructed the 1/12 counterclockwise rotation, or equivalently 30 degrees, because 360 divided by 12 is 30 degrees. And this is just going to be, it's a function from some initial point xy, and the output's going to be, well, n, really n minus n0. So how many times have I moved since my initial time is the total number of 30-degree rotations. So like if n were 12, for example, we should be back to where we started. And you can see the input point shows up here in the x coordinate and there. So the input x goes to both places in both the x and y output, and the input y goes to 2 places in both the x and y output. And let's just recall this entire term before that comma is going to be the x coordinate output, and this entire term after the comma will be the y coordinate output. But just as before, there's going to be infinitely many choices we could make for our initial point. It's not going to do us much to plot infinitely many points. It'll just look a mashup of infinitely many points. So instead we're going to choose a very specific point. In this case, let's maybe go x equals 0 and y equals 1, as well as our initial time being 0, in which case I'm going to replace every x with a 0, so a 0 there, 0 there, and 0 there. That's going to kind of get rid of those first two terms. I'm going to replace every y with a 1, so a 1 there, a 1 there, and a 1 there, and we'll replace every n0 with a 0. So we'll put zeros there. And what we end up with is just negative sine pi over 6n and cosine pi over 6n. And so we're going to end up plotting this collection of an x comma y point for specific values of n. In our case, those values I'm going to choose are precisely 1 through 12, which makes sense because after 1/12 rotations, I should end up back where I start. So let's just see where all of these terms come from. Let's recall we ended up with negative sine pi over 6n, and we ended up with cosine pi over 6n. And so if we evaluate this at, for example, n equals 0, we're going to evaluate negative sine pi over 6 times 0 and cosine pi over 6 times 0. This is going to give me sine of 0, which is 0, and cosine of 0, which is 1. So there's my first point, 0, 1. If I evaluate at n equals 1, I'm going to plug a 1 in here and here instead. So negative sine pi over 6 happens to be negative 1/2, and cosine pi over 6, root 3 over 2. These are kind of the classic points of the unit circle we know. At 2, we'll have negative root 3 over 2 and 1/2, 3, negative 1 and 0, and so on for 4, 5, 6, 7, 8, 9, 10, 11, 12. These are the 1/12 rotations of the unit circle. I don't think it's that surprising. But just as before, how do we actually plot this is we're going to completely disregard all the values of n. And then we're going to imagine that everything for the x and y terms is thought of as a collection of points that we are going to plot individually on the xy plane. So what I've computed here is 12 points in the xy plane, and their output is going to look like, what do you know, the 12th rotations of the unit circle. If we really want to assign our values of n back, recall this was at n equals 0, n equal 1, n equal 2, n equal 3, n equal 4, n equal 5, n equals 6, n equals 7, n equals 8, n equals 9, n equals 10, n equals 11, and in fact at 12 we were back where we started. So if we really do want to think about it as an evolution or an evolving process, we can assign these values just to think about as we're stepping up in n, and as time's moving forward, we do in fact rotate around the circle. Most of the time we don't plot those terms, so we just kind of have to interpret that for ourselves. Kind of just as before, you can get some really pretty images if you choose a lot of initial conditions. In this case, I've chosen kind of the 1/10 demarcation of each quadrant and then rotated all of those by a 12th. And so you get this lovely rainbow unit circle going on. And so hopefully you can appreciate kind of the beauty in this image. That's really what I'm trying to get across with all of my examples today, is by plotting these, we really do see a lot of beauty, and we don't have to focus maybe on the rigor for maybe one section, which is nice. So the next two examples, I'm going to do my best to say that something is also beautiful. And we're going to reserve a rigorous study of 2 and higher dimensional dynamics to other courses. And so if you ever take a course called dynamics or dynamical systems or maybe even chaos or nonlinear dynamics, these are all kind of going to be the same, and you're going to start to study these in some real rigorous depth, but also keeping everything beautiful, because we're going to see even more really nice images show up here. But I will present 2 examples of something that you might encounter in a course on chaos, because these are really quite fascinating examples. First example I have is called the double pendulum. And if you don't really know what I mean by a double pendulum, what we're thinking about is a pendulum swinging from the end of another pendulum. So you can imagine if I have my old grandfather clock here, and it has a pendulum on it that swings back and forth. Then if I decided for some strange reason to attach a second pendulum hanging off the end of the first one, that also is allowed to swing. That's what we're referring to as a double pendulum. And in particular, you can construct really an initial value problem, going back to our previous section, but now it's in 2 dimensions for this double pendulum. And the way the initial value problem looks is you can talk about the acceleration of kind of the first angles. Maybe I should describe what I mean by an angle. Let's draw this out. If I have my first pendulum swinging and it looks like that, maybe the second pendulum itself is swinging and looks like that. When I talk about theta 1, I'm going to draw a vertical through the pivot of the first pendulum. That's going to be theta 1. And if I talk about theta 2, I'm going to draw a vertical through the pivot of the second pendulum, which happens to be the end of the first pendulum, and that's going to be, that angle is going to be theta 2. So this dynamics is most concretely described by describing the acceleration of both of these angles, which I know is a strange thing to talk about, but that's really what makes the writing down the dynamics the easiest. And it still looks a little bit ugly. I mean, you can see this is quite the massive collection of equations I have here. It's definitely not a simple system, but we can describe the acceleration of the first angle related to kind of the cosine of the difference between the 2 angles times the acceleration of the second. We're going to add the sine of the difference of the 2 angles and the velocity of the second squared, as well as the sine of the first angle. That's going to be equal to 0. And you can talk about the acceleration of the first against the cosine of the difference times the acceleration of the second minus the sine of the difference. So that's what's changed. And then that kind of relates to the velocity of the first squared, and then plus the sine of the second. So that's going to be equal to 0. And then these last final 4 terms here, these are just the initial conditions describing the initial 2 angles and the initial 2 velocities. And so if you end up solving this, right, you solve this and you would solve it dependent on these initial two angles, you do end up with, really it's truly described as a dynamics. It's a four-dimensional dynamics because there are two initial positions and two initial velocities, and 2 + 2 is 4. Technically the dynamics evolves in 4 dimensions, but to plot the trajectories maybe of the actual pendula themselves, you just need 2 dimensions. And so you can kind of think about it as a two-dimensional dynamics, and in particular we're going to plot the trajectories of these pendula here. Well, if I go ahead and plot the trajectories, and actually I've put the pendula themselves here before I've plotted them. You can see, here's my double pendulum. I've put it straight up, but I've actually just barely pushed. You can see at the second time step, I've barely pushed that middle part on the double pendulum, kind of the middle pivot, to the right, just the tiniest little bit. And the moment that jumps to the right, because the top one is no longer perfectly balanced on the bottom one, the top one starts to kind of taper downwards. And that's why you can see this trajectory as the next one tapers down. And then, of course, this one has some vertical space, so that's going to fall down that way. And I'm only plotting the trajectory of kind of the red end of it. And eventually that one comes down, the red end swings back up to the right, and you get the resulting trajectory that we see here drawn out in all of these images. So as time evolves, this is how the double pendulum system is going to trace through space, and you do get some really wild images if you trace this all the way out. So that's a very interesting system. But what's even more interesting about the double pendulum is that it satisfies this one mathematical definition, and even physics uses this definition too, of chaotic. And what does it mean to be chaotic? It means if we start two double pendulums from approximately the same initial conditions, so you can imagine if I tried to start them in the same place twice in a row or something, then the trajectories, so the outcomes, will eventually become wildly different. And so even though they started in the same space, maybe as far as I could tell with my human eyesight or something, and they happen to evolve under the same physical laws, right? So it's not like gravity's changing. It's not like I'm swapping out the bearings that they're using or anything. Just based off of their initial placement being just barely different, like a hair's breadth different or something like that, microns even different, the behavior eventually is going to look like you started from two completely different systems. And so to make this a little bit more clear, I've gone ahead and plotted the superposition of two of these. Superposition, not quantum superposition, I just mean like putting two of them on the same image. Initialized from points just 0.01% different from each other. And what we end up seeing is the following. So I've ended up tracing both of their outcomes. My first one is traced in red, and my second one is traced in blue. But of course, when you're watching the video, these are the opposite colors. So I guess cyan and orange. And what happens is they definitely follow the same trajectory right away. They follow the same trajectory for a little bit longer. They still follow the same trajectory for a little bit longer. And they even still follow the same trajectory a little longer than that. And even a little longer than that, because I did put them really close together. But eventually you can see at this 8th step that I've plotted, they are just barely different, right? My red term is right there, and my blue term is right there. And so they're just very slightly different from each other at this point. But if we decide to evolve them after this point, you can see it gets worse. They get farther apart. They get farther apart. And if we look at the traced paths, maybe even over here, the traced paths look almost nothing identical, right? Traced paths are totally different by this point. And really to hammer this in a little bit more, I have actually prepared a nice little coded video. So here I have basically the same system, and then let's watch it evolve over time. So there really are two double pendula here. One is directly behind the other, and just 0.01% so close to the other. And we're going to see them start out together for a little while, but eventually they drift apart. And by the time they drift apart, if you wait a little longer, now they're just all over the place by the very end. So when everything is said and done, you can't really tell that they were even started next to each other right away, because they're just completely drifting into different places. And so these systems are really quite interesting because they do provide a fundamental limit on how predictable the future could possibly be. Because you could imagine if I want to predict the future and I'm measuring everything's position, if my position measurement, if my ruler's bad or something, or maybe my body was shaking too much when I took the measurement, if I'm off by even 0.01%, then the future I predict, right, we don't know which of the two pendula is going to be true in the future, right? The future I predict, I have to make a choice between one of those two pendulum. If I make the wrong choice, then the one I predict is completely different from the one I realize. And so it provides a fundamental limit, and these systems are quite interesting to study because we would like to know about that fundamental limit. And then the next example deals with the complex numbers. And so there's multiple reasons why I introduce complex numbers in this class, but this is one of them. It's just a very interesting example of a discrete dynamics in 2 dimensions. And so let's recall how to compute the square of maybe a Cartesian complex numbers. This is where it's written as x plus iy. If I square it, I'm going to FOIL things out. My i's are going to, I'm going to have one term with I squared. That's going to give me a minus y squared. And so the output of my x basically maps to x squared minus y squared after one step of squaring it, and my y ends up mapping into 2xy. So that's how you can think about this as a two-dimensional dynamics if you end up squaring something repeatedly, because the x itself maps somewhere, the y itself maps somewhere. But in particular, the dynamics that we're going to look at is an initial value problem. We're going to look at this initial value problem, and it's going to be that the change in a specific sequence, so the finite difference of my sequence, will be the sequence squared minus its current value plus the initial condition. That's going to be true for all future times, and then my initial position will just be some complex number, right? Some original complex number. And if I want to, I can actually write this completely in terms of two-dimensional dynamics. So if I want to think about it in terms of an x and a y as an initial value problem, then the change in x is going to be, because I know how to square, my x plus iy, I get x squared minus y squared. So it'll be the current value of x squared minus the current value of y squared minus the current value of x, because we had my minus the n. I'm going to add the initial value of x back in. Or my change in y could be, because of this 2xy, it'll be twice the current value of x times the current value of y. And of course, because of this minus z, I'll subtract y and add the initial condition on y. So this is truly a two-dimensional initial value problem. Let's say two-dimensional discrete initial value problem. We can start our x component as the real part of some complex number and the y component as the imaginary part of some complex number. We're going to ask a very special question about this sequence. What we're going to ask is, for which initial values, so for which complex numbers, does our dynamics remain bounded? And by remain bounded, I'm just saying maybe not tend toward infinity, right? We're squaring something. If I take 2 and I square it, I get 4. If I square that, I get 16. If I square that, I get 256, I believe. If I square that, I don't even want to do it anymore. But that number's getting huge really fast. And so squaring something makes a lot of numbers quite large. For something like 1/2, you square 1/2, you go to 1/4. Square 1/4, you go to 1/16. 256. So anything less than 1 definitely gets smaller and smaller, closer to 0. Anything bigger than 1 goes out to infinity. But we're not quite squaring here, right? If I look at my initial value problem, my change is not equal to the square. It's the square minus itself. So that could do something to it. And actually, I'm adding the initial point here as well. So something other than exactly squaring is going to happen. That's what's going to make it a little interesting. And so, as an example, if we consider an initial value like 1 plus I, for example, you can calculate some future terms, like the next term, z1 will be 1 plus 3i, z2 will be minus 7 plus 7i, z3 will be 1 minus 97i, z4 negative 99407 minus 193i, and z5, this giant collection of numbers, it does not look like this initial condition I've grabbed, 1 plus I, is going to stay bounded. And we're not going to prove that right now, but gives you an idea that maybe some numbers don't stay bounded. But let's say maybe I'm going to divide that previous one, which was 1 plus I, maybe I divide that whole thing by 3, and then I look at where it ends up. Well, after one step, I'm at 0.33 plus 0.56i. After 2, I'm at 0.414 plus 0.7i. At 3, negative 0.14 plus 0.52i. At 4, I'm at 0.08 plus 0.18i. And at 5, I'm at 0.31 plus 0.36i, which is kind of ironically pretty close to these two numbers. That wasn't what I planned to do when I chose these points, but after 5 steps, we basically haven't moved at all, right? This is kind of hovering around. It's moving to a few different points in the complex plane, so it's hovering around a little bit, but it's not. It certainly doesn't seem like it's jumping out towards infinity. It's kind of just hovering around and doing its own thing. And so we're asking questions of like which of these initial values are going to remain bounded. And if we go ahead and plot the ones that remain bounded in red and the ones that don't remain bounded in white, here's my complex plane. This is x, or the real part of my initial value z, and we've got y, which is the imaginary part of this initial value z. And we plot all of the ones that remain bounded after an infinite number of steps. We arrive at like this really fascinating structure here, which is called the Mandelbrot set. So we've got this really interesting, it's got like a heart-shaped looking thing in the middle, kind of, and all these little babies that are jutting off of it. It kind of looks self-similar. In fact, it is self-similar. This is a nice example of a fractal. And you can see our 2 points that we were working with earlier. Here's my 1 plus I point. That's very clearly outside of the set. And then we've got this kind of 1/3 plus 1/3 I. That's kind of just on the edge of the set as far as we can tell here. If I go ahead, I'm going to go ahead and zoom in kind of on this portion of the graph just to show you how the fractal nature looks. And there you can see that 1/3 plus 1/3 I sitting inside of the Mandelbrot set just a little bit. But you can see it's still, no matter how much we zoom in, we're getting this crazy behavior on the boundary of this set, just deciding which initial conditions are going to remain bounded and which ones aren't. And so this is a cool example of a fractal. And the definition of a fractal is one of those for which if you decide, you start out with a jagged boundary, but even if you zoom in, you're not going to get any sort of a smooth boundary. A lot of times, like I'm looking at my table right now, the corners look jagged, or at least sharp, but if you look, if you put a microscope up to those corners, they'd actually be kind of round at some point if you zoomed in, but fractals aren't going to satisfy that nature. So no matter how far you zoom in on a fractal, you're still going to see jagged edges. This is a cool example of discrete dynamics, and we're going to stop there for today. I just wanted to give you a couple great examples, very artistic examples, and some motivating examples for why we do actually care about plotting and interpreting the evolution of two-dimensional points in planes. Anyway, I'll see you in the next one where we're going to talk about parametric curves. Bye.